Hey everyone, Mr. Andrew here. Today I want to talk to you about polyatomic ions. Polyatomic ions are groups of atoms that are bonded together through covalent bonds. And when these atoms are bonded together, they act as if they were one single ion. Now, these polyatomic ions come in all different formulas. You can see a table of them right here. Okay, these are some of the most common polyatomic ions. There are actually a lot of polyatomic ions. There's like more than 50 polyatomic ions. And as you can see, they all have different formulas, they all have different charges, and they all have unique names. Now, these polyatomic ions can be used to form ionic compounds in the same way that the monoatomic ions that you're used to can be. And there's just a couple of key differences that I wanted to talk to you about today. So let's look at a couple examples of polyatomic ions. Let's start with a pretty straightforward example. Let's say we wanted to form an ionic compound that was made from sodium and carbonate. I guess I should just write out the name. Okay. If we were to write out the ionic symbol, sodium being monoatomic is pretty straightforward. Just Na, and it's got a plus charge. We know it's got a positive charge because it is a group 1 element. Carbonate, if we look right here on the table, is CO3 2 minus. So 1 carbon and 3 oxygens bond together, and they have a -2 charge when they do this. So I want to write a formula for an ionic compound. Okay. So to do this, I'm going to do the crisscross method here. So my 1 from sodium is going to become a subscript for CO3. My 2 over here is going to become the new subscript for sodium. So my formula is going to be Na2CO3. Okay. And if we check the charges here, CO3, that has a 2 minus charge. Sodium has a 1 plus charge. But because there's 2 of them, that's 2 plus overall. Which means we can now see 2 plus and 2 minus 2, that's equal to 0, and we are neutral. So this is the correct formula, Na2CO3. The name for this is going to be sodium carbonate. Okay. So ordinarily, with monoatomic ions, the anion, you have to change the name to the IDE form, okay? But because we have a polyatomic anion, the name stays the same, okay? We don't change this to carbonide or anything like that. We just leave it as carbonate, okay? Let's look at another one. Let's look at let's do calcium. Or actually, no, let's not do calcium. Let's do ammonium, and let's do oxygen. Okay. Now we have a bit of a different situation here. So ammonium right here is NH4, and it's got a +1 charge. Oxygen, because it's a group 16 element, will have a -2 charge. Now we do the crisscross method. That's a 1, so that goes over here. This 2 goes over here. Now, we have a bit of a problem because this 2 is supposed to apply to this whole thing. So, how do we communicate that? Okay, we want there to be a 2 right here, but we need to show that it's going to apply to this whole ion. So, the way we write this out is NH4, we put it in parentheses, and then we put a 2 on the outside. So this 2 subscript right here is saying that everything in the parentheses is going to be copied twice. Okay? Then we just have an O. The O has a subscript of 1, so we just leave it alone. Okay? So if we double check the charges on this, NH4 that has a 1+ charge, and there's 2 of them, so it's a 2+ charge overall. Oxygen is 2-, and so now we're balanced. 2 minus 2 equals 0. We're neutral. The name for this is going to be ammonium. And then the anion is monoatomic, so we have to change it to the IDE form. So oxide. Okay. Now, sometimes the parentheses right here can be a little confusing for people. Okay? It's kind of hard to visualize this. So let me approach a similar problem in a slightly different way, and maybe this will help you out. Okay? Let's say I had calcium and acetate. Okay? So calcium is Ca2+, because it's right here. It's a group 2 element. And acetate is CH3COO-. Now, you might sometimes see acetate as C2H3O2-. And if you total these up, you'll see that they're actually the same as each other. So it really depends on who's writing it, which way it looks. Okay? But for the sake of consistency, I'm going to write it the same way as it appears on this table, which is right there. Now, I'm going to borrow a math strategy. And the strategy I'm going to borrow is substitution. Okay? What I'm going to do is I'm going to say that CH3COO is going to be just represented with an X. Okay? And you'll see why I'm doing this in a little bit. It's for simplicity. So I'm going to replace my formula right here. And I'm just going to call it X. And I'm going to clean this up a little bit. Okay? So the charge is remaining the same here. I've just replaced all the atoms with an X. Okay? And I'm going to change it back later. But for now, I'm just going to leave it this way. Okay? So I'm going to do the same crisscross method. Okay? The 1's going to go over here. The 2 is going to go over here. And my formula is going to end up being CaX with a 2 right there. Okay? Now, what I'm going to do is I'm going to now switch this back. So I'm going to erase my X right here. I'm going to move my 2 out a little bit also. And in parentheses, I'm just going to write the formula that I swapped out. CH3COO. Okay? This is the correct formula. If we double check this, CH3COO, this is a 1 minus charge, and there's 2 of them, so that's 2 minus total. Calcium is 2 plus. 2 minus 2 equals 0. We're balanced. Okay. My name, the cation, calcium, stays the same. And the anion, because it's polyatomic, is just going to also stay the same. So my name for this is calcium acetate. So hopefully this gave you a better understanding of polyatomic ions and just the idea that they function as a singular unit that isn't broken apart during these reactions. If you have any questions, feel free to stop by and ask me anytime, and I will see you next time.